Okay, welcome everyone to IAMA 2023. I'm Faye McNeill. I'm one of the co-lead organizers of the conference this year, along with Andy Zund. And we're excited to be here in Davis this week to discuss aerosol modeling algorithms. I'll give you a few tips on the slides here. Oh, okay. All right. First, I wanted to get started by thanking the Technical Program Committee. This is the real reason why these meetings are so wonderful. We draw on the community and its expertise to really bring the hottest topics to this conference. So thanks to everyone who's participated in putting together the technical program this year. Okay, just a few housekeeping notes about the exits and the restrooms. Please silence your cell phones. And also, if you're not feeling well, stay home. I also noticed that there are some N95 masks available at the desk if anybody needs one. And we do have about 10 virtual attendees this year. If anybody needs assistance, please feel free to reach out to Kelly and Sandra. We have a welcome reception this evening, which is also part of the integrated with the poster session. That'll be just here. Please stick around after the sessions today. So, we're lucky to be in person, many of us today, and it's a relatively intimate group. So we will be taking questions from the floor just with microphones. But we also have the Slido system, which is great for allowing the virtual presenters or the virtual attendees to participate. And also some of us in person may want to use that as well. The instructions for doing that are here. Basically, you just visit slide.do in your web browser, and then each session will have its own event code, which we'll present at the beginning of the sessions, but also they're printed in the program. So you can see at the beginning for each session, there's the specific code for that session Slido. So it's pretty self-explanatory once you get in there, and you can let us know or let Sandra know if you have any questions. But as I said, we'll be also taking questions just from the floor. And we even have these paper question submissions also. Huge thank you to California Air Resources Board, CARB, for sponsoring this event, and AQRC. Wouldn't be possible without their support. And with that, I will introduce Dr. Sarika Kulkarni from CARB, who will say a few words on their behalf.
Thank you, Faye. Good morning, everyone. On behalf of the California Air Resources Board, we welcome you all to IAMA 2023. A brief history of these biennial conferences that are sponsored by CARB. Atmospheric chemical mechanism. The history started with Atmospheric Chemical Mechanism Conference in 2006. Which was in response to Bill Carter's retirement announcement. For those of you who don't know Bill, he's the lead developer of the SAPRAC chemical mechanism, which is the chemical mechanism used in California for all of our regulatory modeling efforts. After the success of ACM in 2006, it was decided to add a second conference specifically focused on aerosol mechanisms and modeling, and IAMA was born a year later in 2007. The idea behind IAMA is to bring together experts from around the world who are working on different aspects of aerosol science and modeling to share their work and ideas. The ultimate goal is to improve the representation of aerosol physics and chemistry in the chemical transport models that form the scientific basis for much of the work in the regulatory air modeling community. Although IAMA and ACM started as two distinct entities, over time, the lines have blurred as our interpretation of organic aerosol and chemistry has evolved. And they are now very much complementary to each other, and quite often than not, you will see many of the same attendees at both IAMA and ACM. The main justification for starting these conferences is to support the underlying science used in the state implementation plan process, which hinges upon the photochemical modeling to assess the emission reductions that are needed to attain ozone and PM 2.5 national ambient air quality standards. Of course, there are other components that are important to photochemical modeling beyond what is covered at ACM and IAMA, with the most important being meteorology and emissions. While emissions inventory can be a sensitive topic, meteorology is not. And so in 2013, the McNeill Meteorology and Climate Modeling for the Air Quality Conference was added. The idea behind McNeill is to bring together meteorologists and air quality modelers to put spotlight on meteorological issues that are particularly important to air quality, but may not necessarily be a major focus in the general meteorological community. As CARB uses these conferences in two ways. One is to gauge where the academic research is going, so we can better plan for the future, and as a way to inform all of you about issues or concerns that are relevant or arising in the regulatory community. In 2018, we added ASIC, the Air Sciences International Conference, to the list of this biennial conference supported by CARB. ASIC focuses on the development and use of low-cost air sensors for air quality applications. With that brief history, it's time to kick off the IAMA 23 talks, and might get pressure to introduce the first keynote speaker, Professor Jeffrey Pierce from the Colorado State University. He's a prof at the Department of Atmospheric Science. His group's research focuses on atmospheric aerosols, their physical and chemical evolution in the atmosphere, and their impacts on climate and human health. They aim to blend the models and observations to learn cool new things. He currently serves on NASA's Health and Air Quality Applied Science Team HACAST, and is an author of the current US National Climate Assessment. Without further ado, please join me in welcoming Jeff for the first keynote talk of the day.
Thank you so much, and really thank you to the organizers. This is just very kind, and happy to start things off here. So yeah, thank you so much. So I'm going to, kind of get at a few of the aspects of the challenges in representing biomass burning aerosol in models. There's many, and I'll make that point. And we'll sort of come into some of the ways we're working on some of these challenges. I want to start off by acknowledging the people who actually did the work. And so the bulk of what I'm going to show today in terms of new research was done by Nicole Junes, a current PhD student in my group. She'll be looking for jobs next year. So just keep her in mind when she'll be on the job market. And I'm also going to show some early results by Kim Sakamoto and Emily Lamarine, who are former students in my group. And I need to acknowledge lots of amazing collaborators. There's several papers I'm going to show here with many, many different collaborators on those as well. All right, so I'm going to show this animation quite a few times. So this is a loop of true color image from Goes West over Colorado during the fire season in 2020. This is from August 15th. And there's 4 major fires happening on this day that are all listed here. And so they're all coming out of these. And then these are, confusingly, these are convective clouds. So there are also thunderstorms happening on the eastern plains, but only the smoke's coming out of the 4 places with red dots. So I want to use this as an example to point out some of the ways that smoke is challenging to represent in models. So I've superimposed on here what might be a typical model grid. So if you're running a global aerosol model and your resolution is 200 kilometers by 200 kilometers, you'd have this green grid box. And notice how these full fires are all within the grid box. Some parts of the grid box are completely not smoky at all, and some parts have very high concentrations. And even if you're running a regional model at say 25 or 50 kilometers, you still have a lot of variability within that. So one thing to focus on is this subgrid concentration variability in smoke. This is a really big challenge for models, and we're going to dive into this today. Plume injection height is also really challenging to get in models, and we'll look at this a bit more, but you can sort of see throughout the diurnal cycle, every now and again, these fires will burp out something up into the free troposphere, or upper troposphere, and I'll point out, you can actually see one right there, and you can see the shadow beneath it. It's wild. But yet a lot of the time it's emitting smoke to the boundary layer, so it's at the surface, but how do we even get that? But color, you can see the smoke's kind of gray. Sometimes it looks whiter. That could be because there's a cloud on it, but representing that right is challenging. There's this huge temporal variability in emissions. Right now, the fires aren't emitting that much. And then throughout the day, as the smoke gets more, as the sun gets more intense, the air gets hotter, the wind speeds in the boundary layer pick up, the emissions will pick up as the fires intensify. And one thing we'll talk about a bunch is that different plumes tend to dilute at different rates. And so you can have some plumes that maintain high concentrations, other plumes that maintain low concentrations. And so to further make that point, this is just now a still true color image from satellite with many different fires over the Pacific Northwest. And you can see things where you have like big plumes from large fires that maintain their concentration as they move away. If you have a large fire and the plume is, let's say, 100 kilometers wide, it's really hard to get clean air from the sides to mix in to dilute that core, and the concentrations will stay high in that plume for a long time. Whereas in this case, this is just a single fire hotspot. Small fires, if I dilute a match in this room, it's going to dilute very quickly. Even if the emissions per meter squared of my match are very high, it doesn't take long to mix clean air into that small plume. And also there's these challenges of, you get big plumes that merge with each other and make super plumes. And so keeping track of these things is challenging. And then the biggest issue, like I pointed out before, is when we put this all into a grid box, almost all of the time, we just dilute that smoke instantly within the grid box. So you have this plume that has this high concentration, we put it in our model, and then shoot, we take all of those smoke particles and spread them out over the grid box. So if there's any process that depends non-linearly on the smoke concentration, we are not going to represent that right. So I'm going to talk about a number of things now, but I want to just acknowledge, because I know there's a whole bunch of different research and regulatory goals in this room. So the different factors I'm going to talk about, what's important to you may differ a little bit, depending on whether you care about surface PM concentrations for regulatory purposes or smoke forecasting. Then some of these issues are maybe more important than others. Or maybe you are on the detailed aerosol physics and chemistry side, in which case, maybe the actual OA composition matters more than the actual PM mass and that sort of thing. And if you care about direct and indirect radiative forcings and climate simulations, then again, your priorities might change. So I'm just sort of recognizing that there's different goals in the room, and some of these different issues manifest themselves in different ways. Okay, so let's just sort of recap on some of the challenges simulating smoke. There's more than one I'm going to list here, but I'm going to just list a bunch of them. So that plume injection height. So this will help determine how much is at the surface. It's going to probably affect the aerosol lifetime. If you kick it up into the free troposphere, it's probably going to stay in the atmosphere longer. And if you're interested in climate, whether you put those particles above or below clouds is going to affect your radiative forcing. Then there's these subgrid scale plumes issues, which is going to have nonlinear physics and chemistry impact. So it's going to affect coagulation rates. If you take your particles and you spread them further apart, they're not going to bump into each other as often. So coagulation is going to change. Your primary organic aerosol evaporation and your secondary organic aerosol formation is going to be different if you change your concentration of the smoke. And if you are interested in, say, the smoke concentration in Steamboat Springs, which would be somewhere around here, the fact that your smoke is only in certain parts of the grid box is going to make that challenging to actually predict what smoke concentration is locally. It's challenging to get the emissions, particularly the daily cycle and the amount. And then in terms of composition, This can show up through absorption effects, like how much for climate reasons, like how much is are the particles absorbing, as well as health and toxicity. So in interest of time and not wanting to like completely bury everyone in details, I'm only going to talk about a subset of these, just what's highlighted here in red. So it'll be split into two parts, one on plume injection height and one on subgrid scale physics, mostly focusing on coagulation. But I do want to point out that at this conference, I looked through the abstracts and titles. There'll be people speaking on some of these. So Megan D'Alessio is going to be talking on Friday about simulating absorption in models and how that evolves in the atmosphere. And then on the health and toxicity side, Manabu has a talk later today on this. And I put that Havila had a poster because that's what was on online. But I talked with Havila this morning, and she also has a talk today. So we'll be getting quite a few of these aspects that, that I'm not talking about. So let's first think about plume injection height. And before I start, I want to point out that Jun Wang has a talk on this on Friday. And so Jun's done a ton of work on how to use satellites to understand plume injection height. So his talk is going to complement some of the things I'm setting up in here. All right, so now let's rewatch this video and just try to focus on plume injection height in this. And you can see in many of these plumes, it might be easiest to see in this one, that you get a bit of a shadow underneath. Okay, so here we're starting, the smoke's being emitted at the surface. And as the day goes on, the smoke starts getting emitted into the lower free troposphere, you get a shadow. And then every now and again, maybe it's this one, you get this big burp of the pyrocumulus and you see that huge shadow underneath. So that plume's going up to like 10 kilometers. And so within each day, each fire is having some of the time where smoke's getting at the surface, some of the time it's going into the lower free troposphere, some of the time it's going into the upper free troposphere. Holy crap. How are we going to get this into our models properly? And how much does it matter? So if we just like do a thought experiment where we compare smoke, if we just emit it all on the surface in our model versus if we allow for some sort of representation of plume injection height. So just thinking about smoke at the surface versus emitting it aloft. If it's emitted aloft, there'll be less smoke at the surface, at least near the source. If you put it in the free troposphere, it's going to take longer to dry deposit. It's probably going to take longer to wet deposit because you put it over a bunch of the clouds that are raining. And so the lifetime should increase if we put it in the free troposphere. It also is moving faster in the free troposphere, so it's going to go farther in less time. It's going to impact whether those smoke particles that are somewhat absorbing are above clouds. So clouds are very white. So if you put smoke above them, it might be more absorbing than the clouds. And so you could have a warming effect versus if they're below the clouds, then the smoke doesn't matter because the clouds are blocking them. And then eventually somewhere, unless it gets rained out directly from the free troposphere, that smoke will get transported back down to the surface and impact air quality, at least to some degree elsewhere. We wanted to test how big these different effects are. So Nicole ran the Geoschem Tomas model. So this is Geoschem with online aerosol microphysics. So we have size sections, coagulation, condensation, and so on. We ran it relatively coarse for the globe just because it's expensive to run with full chemistry and with full aerosol microphysics, but it still gives us an idea of the global effects of some of these things. And so we can do this now because the GFAS emission inventory, along with providing the emissions rates of smoke OA, smoke black carbon, and all the gas phase species, now includes with it information on plume injection height. And so when developing the inventory, the folks that put GFAS together take fire rated power from satellite, as well as thermodynamic temperature profiles of the atmosphere, and run a model and come up with information on their estimated plume injection height. And they provide an estimate of where the bottom of the plume is, the top of the plume, as well as the mean height of maximum injection, so where most of the smoke is going to be. So this is great. So we can actually just take this directly from the emission inventory now and put it into the model as an estimate for smoke injection height. So we can compare cases to where we emit smoke at the surface, which is often what we had done before for Geoschem Tomas. So this is a case where we would emit at the surface all the time, versus when we have the GFAS information on where we should be emitting the smoke from the plume bottom to the plume top. However, there's been some evidence that the GFAS plume injection heights are too low, at least for some big plumes. And so this is a case study by Walter, where the GFAS mean height of maximum injection is this green line, and the plume top is the red line. And notice that here it's 2-day averages, although GFAS actually gives 1-day averages. Whereas Walter ran plume injection height more finely throughout the day. And with the plume injection heights peaking in the middle of the day when the fires are most intense, things go up. And then with lower injection heights overnight. And you can see, particularly here, the midday injection heights are quite a bit higher than what GFAS is providing. And this is also when most of the smoke emissions is happening. So there's some evidence here that the smoke may be being injected too low by GFAS. And part of this could be because fire radio power, when detected from satellites, if you have a large fire, it's hard to actually see the fire itself through the smoke, and the fire radio power estimates could be too low. So somewhat arbitrarily, we wanted to modify this. So what we did is we increased the plume injection height in GFAS by moving the bottom of the plume to the previous height of maximum injection. And then we did it again, we increased it a second time when we moved the bottom of the plume to the top of the plume. So super arbitrary here. And we know we're not actually good on any given plume, we're not going to expect to do better. But we wanted to see what's the sensitivity of a model simulation to shifting it up. And sort of on a global scale, is it actually getting the plume heights better? And so for testing whether or not increasing the plume height is on average better, Nicole did this comparison against Calypso LiDAR profiles. And so she's limited here LiDAR profiles, so this is spaceborne LiDAR, to times when the model thinks that at least half of the aerosol optical depth is from smoke. So eliminating all the times where smoke has a smaller influence. And so what's shown here is this is the extinction profile from Calypso as a function of height from the lower free troposphere, from the boundary layer to the upper troposphere. For global, for the contiguous US, as well as boreal North America, so Alaska and Canada. And so this is for a simulation where we have no smoke on. And so it makes sense that we've limited the cases where we know smoke is impacting, and we run the model with smoke off, we are going to underestimate extinction, all these different locations. If we then turn on smoke but emit it only at the surface, so it's mostly limited, confined to the boundary layer, sometimes it may be able to mix out because of convection or large-scale meteorology, we tend to underestimate, particularly in the mid-troposphere. And now our 3 different cases where we include plume injection heights. So this is what is included within GFAS. And so in which case, most of the time, GFAS plume injection heights are still within the boundary layer. So for global and for CONUS, that doesn't actually make much difference. The purple is right on top of the green line. But for Canada and Alaska, we're actually starting to get some improvement in the mid-troposphere. So then when we arbitrarily shifted it up once, we maybe started to get a little improvement here and then even more improvement in Canada. And then when we shifted up a second time, you can see we're starting to fill in this tropospheric gap. And so this is some further evidence that perhaps the plume injection heights within this inventory need to be shifted up further. But again, we're sort of doing this in this arbitrary way. We don't expect that it's physically better. We're just sort of tuning it, cranking it up in terms of injection height. So what effect does this actually have on some of the things that matter to us, like surface PM 2.5 or radiative effects? So this is the global 2-year mean surface PM 2.5 from smoke or biomass burning specifically. So this is not total, this is just from wildfires. And you can see that these areas in red get up to about 10 micrograms per meter cubed, and this is the expected source regions. So boreal North America, boreal Asia, the tropics, and some in the contiguous US, so to dominate this. If we then take this and we, this is where the emissions are just at the surface. And so now when we consider plume injection height, this is our case where we use the GFAS injection heights, and then we're shifting up and shifting up again. This is the percent difference in the surface smoke PM 2.5 relative to this case. So what you see is happening is in the source regions, you can see it most strongly here, and all the places where there are smoke, if we increase the plume injection height, of course, we're going to reduce the surface smoke in those locations. Not a big surprise. But we're then getting these big relative changes in smoke in remote, particularly marine regions and marine subsidence regions, where we're getting up to a doubling of the smoke. These are places that don't have a ton of smoke to begin with, so it's not a huge effect in absolute sense, but in terms of the relative change, it makes a big difference. So you're lifting it up at the source region, lowering PM 2.5 then there, and then increasing PM 2.5 in remote regions. All right, so now thinking about aerosol optical depth. So this is the measure of the extinction throughout the whole column, and it's roughly proportional to the mass of aerosol in the whole column. So before we were just talking about surface PM 2.5, now we're talking about aerosol in the whole column, so starting to move towards radiative effects. And so this is the biomass burning specific aerosol optical depth just when we emit at the surface. And you can see, again, our source regions show up most strongly as having the highest aerosol optical depth, with that smoke then being transported elsewhere. Now, if we look at the impact of raising injection height in these cases, we get almost an increase everywhere around the globe. Maybe a little bit of a decrease in source regions just because we're putting it in the free troposphere and the winds are faster. But overall, we're getting relatively big increases. And this is driven by putting it in the free troposphere, the smoke stays in the atmosphere longer. It has a longer lifetime, and it's allowed to transport further. It's away from deposition sources. And so we end up with more smoke in the atmosphere. And so climatically, we would expect that this gives us the potential for bigger climate effects. Thanks, Andrew. All right, so this is just now to build off of aerosol optical depth. This is our predicted direct radiative effect due to biomass burning. And you can see to some degree, it's like similar in terms of what places are strongest to our aerosol optical depth. However, we get changes in sign. So when that aerosol, the smoke is over dark surfaces like forests or oceans, you get a cooling effect. So the smoke is more scattering than the surface below. But when the smoke is at high latitudes where there's snow and ice, you end up with a warming effect. And so that's why in the northern latitudes, that boreal smoke can have a warming, because you put somewhat absorbing smoke over ice, sea ice, land ice, snow, and you get a warming effect. Overall, smoke is cooling, though, with about a 0.1 watt per meter squared cooling. Now, to increase our plume injection height, to first order, these effects just intensify because there's more smoke in the atmosphere, it's staying in there longer. But there's some places where there's a cooling effect here, and then by raising it up, there's an overall warming effect relative to the surface case. And so why is this? If we're putting more smoke into the atmosphere, why in some places where we had a cooling, are we cooling less by having more smoke in the atmosphere? And the reason for this is we're now putting smoke above clouds in places. So places where there's a lot of low clouds where we can then inject smoke above it. If you see the smoke here above the dark surface, it's clearly brighter. And so that it's taking energy that would have been absorbed, solar energy that would have been absorbed by those trees, and it's now reflecting some of that back to space. However, when you put it over bright surfaces like low clouds here, you can see that the smoke looks darker than those bright clouds, in which case, instead of those clouds reflecting sunlight back to space, we now have smoke that's somewhat absorbing. And so this is showing a profile, the global cloud fraction. So read off the top plot here, and then this is the cloud fraction with the low cloud peak here. And so by shifting to increasing our plume injection height, this is just relative to the surface case, how much extra biomass burning black carbon do you get? And so by shifting your plume injection height more, you're putting black carbon above the low clouds, which is allowing for a warming effect from that. So we're going from a case where almost all the smoke is below all the clouds to cases where now allowing smoke that's somewhat absorbing to be above clouds, which is dampening the effect of smoke cooling. We also assess indirect effects, but I'm going to skip today for time. So just to sort of summarize, we found that there's less smoke at the surface near the source. If you put it, when you inject in the free troposphere, when you have these high plume injection heights, the aerosol stays in the atmosphere longer, but it allows the smoke to go above clouds, which can increase the warming due to smoke. And then eventually you mix that smoke down, changing the surface PM concentrations in remote regions. And again, I want to circle back to June's talk because I just sort of set up, hey, here's the problems with plume injection height. And then June, I'm expecting on Friday, you're going to talk about the stuff you do with satellites that is going to help us actually improve this in models going forward. All right, so now talking about this subgrid issue. So you got like anything where there's nonlinear physics and chemistry that depends on smoke concentrations, you're going to get a different answer if you change your smoke concentrations for whatever reason. I'm going to focus on coagulation today for time, but I do want to give a shout out to Shantanu Jathar. So Shantanu and I have worked together quite a bit on trying to understand how smoke dilution affects primary organic aerosol evaporation and secondary organic aerosol formation. And there's many other people that are working on this too, including people in this room. And so this is super important as well. I just don't have time to talk about it. But we're happy to talk about it offline if you're interested in that. Okay, so just sort of reiterating this point again, we have these model grid boxes and we're emitting smoke into them. And so there's two issues here related to how we change concentrations of smoke. So one, we have smoke that instantly mixes into our grid boxes. And two, real smoke plumes dilute at different rates. And so some smoke plumes are going to go down to 20 micrograms per meter cubed within an hour. Other smoke plumes are going to stay at 1,000 micrograms per meter cubed to PM within an hour. And so that's we're talking orders of magnitude differences in concentrations for different plumes. So just first thinking about the smoke instantly mixing into the grid box, to motivate it, just think of it as like this. I mean, this grid box is probably deeper than it should be, but imagine you have multiple fires within a plume and they're each maintaining high concentrations. But the way we do things is we just take those particles and we instantly spread them apart, lower the concentrations into our grid boxes. Doesn't matter whether you are regional or global, there's some of this dilution happening. And two, real smoke plumes dilute at different rates. And this is, I think, an underappreciated part of smoke modeling. And so I like to think about it as like driven largely by fire size differences. And so this is from the EPA's NEI in 2014. They nicely had an inventory of fire area burned per day. And so on this axis, this is kilometers squared burned within a day. And this is essentially a fire size distribution or a histogram of how many fires is a different size. So this spans 8 orders of magnitude in fire size and fire area. And then this is just a count in log scale. So with the peak sort of being in these sort of mid-fire sizes. But what are these fires actually like? Can we get an appreciation for these fire sizes? So these largest fires here are the ones that you can see as complex fires, as multiple hotspots, like very obvious plumes coming from them. These often are in the size of like, a size of a city burning within a day. Hopefully it's not a city, but it's, that sort of area that is burning. These ones here that are on a kilometer per day, these ones generally get hotspots, but there may be 1 or 2, and they're maybe a little bit harder to see the plumes, you see them dilute more quickly. As we move down, we start getting into prescribed fire range, football field size, is still represented on here. And then we start getting into like bonfire size at the end of this emission inventory. And these are probably supremely undercounted in the inventory, because how do we keep track of the number of campfires? We don't. So it starts falling off here, but there's probably a whole lot more. So think about that, the differences in the fires. It's just amazing the huge span in fire sizes. So what does this actually mean for concentration though? So what we did is we ran just dispersion calculations for different fire sizes. And so this is showing the dilution ratio for these different sizes, ranging from our biggest fires down to the smaller fires in the inventory. And so imagine these big fires, they have these wide plumes. It's very hard to get clean air to mix into the core of the plume because it's so wide. And so in our big plume, all the dilution ratios start at 1. And then for the biggest plume, after 8 hours, it's only down to a dilution ratio of 2. So what this means is if we start with like 1,000 micrograms per meter cubed at time 0, which is typical for a very fresh room. So 1,000 micrograms per meter cubed, after 8 hours, it's only going to have diluted down to 5,000 micrograms per meter cubed. Wicked high concentrations, but that's expected for a very, very large fire. If you sample it, several hours down, you're still above 1,000 micrograms per meter cubed. As we move to smaller fire sizes, those dilution ratios increase by orders of magnitude. So as we move down, like let's say to our smaller ones, we're over 1,000 or over 100,000 dilution ratio. So if we started at 10,000 micrograms per meter cubed, you're well under 1 microgram per meter cubed 8 hours downwind. And that makes sense. If we lit a campfire outside and you try to track that plume and you're 8 hours downwind, it's going to be really hard for whatever instrument you're sampling, like whether it's a AMS or whatever, it's going to be really hard to find a campfire plume way downwind. It's just too easy to mix in with the clean air. So how do these two issues affect coagulation? I'm just going to focus on coagulation, but you can sort of generalize this for other nonlinear effects as well. So in coagulation, what it tends to do is you have particles, they bump into each other. So you reduce particle number because every coagulation event, you take two particles, you make one, but you make a bigger particle. So it increases the median width of your size distribution. So this is just a dNd log dp and a simple calculation I did with 3,000 particles initially, particles bumping into each other. After 10 hours, you see the number under the curve, the total area under the curve has gone down and we've shifted to the right, as well as it makes your log normal width narrower as well. It's highly dependent on concentration because we're talking about particles bumping into particles. So each particle needs more particles around in order to bump into it. So coagulation goes with the square of number. So if we go from 3,000 particles per centimeter cubed down to 1,000, the coagulation rate slows by a factor of 9. And so you can see there's this coagulation here, it's significantly smaller in this case. So if you change your number concentration by a factor of 10, your coagulation slows down by a factor of 100. It's super nonlinear. And we'd expect large fires that we just made the point with large plumes that aren't diluting to maintain high concentrations, to have higher coagulation rates, and small fires where your dilution happens quickly to have much less coagulation. So if we're just thinking in terms of particle size, we'd expect much less of a shift in particle size for smaller fires. And particle number, we're going to have much less decreases in particle number, not due to dilution, but due to coagulation itself. So what Nicole did is to try to find this result in the real world. And so she went into FireX AQ data and found 8 cases where there was some sort of pseudo-Lagrangian sampling of fires as a function of age. So this is smoke age for one specific case where there's 1, 2, 3, 4, 5, 6, 7, 8 different times the plane crossed the plume downwind. And she calculated what the median diameter of the size distribution was in those cases. And it was growing every time it went downwind. If we take away the noise, it's growing. And in this case, it was growing at 11 nanometers per hour. From this alone, we don't know that that's coagulation, but she will test that. And I'll show that in a slide or two. So this is now all 8 of those cases. So this is that plot I just showed, and then 7 more. And this is a range from the plume with the lowest concentration at the first transect. So one where we'd expect dilution to have already happened quite a bit. Increase in concentration, increase in concentration. So we went from 45 micrograms per meter cubed up to 2,000 micrograms per meter cubed here. And as you can see, up in this top row, the particles are only growing after several hours to like 170 nanometers. And down here, we're getting up to like 300 nanometers. So anecdotally here, there's this pattern that with the higher concentrations, you get push those particles to bigger sizes, some evidence of coagulation. So what Nicole then did to further test this is she ran a model. So this is a different plot than this one. So this is just trend lines. Now the lines here are model lines. And so in each of these cases, Nicole ran a model where she was only simulating dilution and coagulation. No SOA chemistry, no PLA evaporation, or any of those details. Just keep it simple. Just dilution following what was observed and let the particles coagulate with each other. And you can see for most of these cases, the model follows the trends quite surprisingly well. In this case, it doesn't get enough growth. In this case, it follows the growth, but then I think the plane wasn't Lagrangian enough in this bit and was sampling smoke that was emitted earlier and the particles get smaller. I don't think that's real shrinkage. I think that's just the way it was sampled. But for the most part, the model's getting that. And if we plot the model that only had coagulation and dilution against the observations, and this is the growth of size in nanometers an hour, for all but that one first case, it's representing that incredibly well. So this is showing that by concentration and dilution rates and so on, that's determining how much these particles are growing within the case. And in following that, it's how much also number is reduced because the ones that have had the most growth have the most reduction in number. So they're getting the bigger sizes at the expense of particles going away. So this is in the real data, but can we represent this in our 3D models? So again, we have this case where we instantly emitting into the grid box, and we're missing these details entirely. So this is what we typically do in our models where we take our fires and instantly mix them. And so if we actually have the coagulation within these plumes, we'd expect more than if we took it and we moved all our particles apart from each other, and then they're kind of just drifting around the Brownian motion and then not bumping into each other. So coagulation's happening way slower when we dilute it into our grid boxes. But what we really want to do is, can we find a way where we can estimate how much coagulation should have happened in those plumes when they were most concentrated, figure out what the size shift is, what the number reduction is, and then put it into our grid box after we've sort of pre-processed it. So this is what Kim did. And so she ran lots of plume dilution, coagulation calculations, and came up, fit it with a simple parameterization where we wanted to come up with what's our median diameter of smoke after we allow for some subgrid coagulation in the plume as a function of some emitted median diameter. And then we have 3 fitting parameters that Kim fit against all of her numerical calculations. And these 3 factors that can come in from 3D models. So we have total emission rate. As this goes up, this B is a positive parameter. So emissions go up, the size of your median diameters goes up. So this emissions, this is like kilograms per second. Could either come from a larger fire or a higher emission flux. But either way, it's going to increase the coagulation and increase the diameter. If you increase your wind speed, that means the air passes over the fire for less time when you have lower concentrations. And so our final diameter, we'd expect less coagulation. And so this lowers it. And then mixing depth is just another form of dilution. And this is again going to decrease your final diameter. And the one parameter we kind of have to guess on for our model is how much time we want to allow the subgrid processing to happen for. We usually do 5 hours or so. Unfortunately, this C parameter here is like 0.3 or 0.5. And so the further you go out in time, the less time matters. But the further out for time, the more growth you get as expected. So we put this through, we process it for like 5 hours, and then we put it back in the grid box saying, okay, this is the plume process size, and it reduces the particle number as well. So what Emily did is she put this into the Geoschem Tomos model, just similar to what Nicole did. And she ran the model with and without this emissions pre-processing for the subgrid coagulation. And we could see huge changes in certain parts of the atmosphere. And so this is for Alaska during the biomass burning season. If we turn smoke off, this is the size distribution in green. If we turn it on without subgrid coagulation, we get this peak that's around 100 nanometers with quite a few smoke particles. But then if we allow those particles to coagulate in the plume, we get the shift to like 250 nanometers. So the particles are larger. The area under the curve is lower, so coagulation has reduced number, but we've made them bigger. And then in the Amazon, we see a similar amount of impact from biomass burning, but there's actually less of an effect due to subgrid coagulation. And that's because the fires in Alaska tend to be huge and they don't dilute very quickly and they maintain high concentrations. And so they get a big shift, where Amazon fires tend to be smaller. And so they're at lower concentrations, so there's less subgrid coagulation. In terms of impacting radiative effects, this is comparing the radiative effects of biomass burning when we have no subgrid coagulation on to when we do. The direct effect has a minor enhancement in cooling because we have shifted the particles to larger sizes where they have a stronger scattering efficiency, mass scattering efficiency. But the indirect effect, though, we cut in half. And that's because that subgrid coagulation reduces number, it reduces CCN. And so it really sort of shuts down the aerosol indirect effect due to biomass burning. And so the last thing I want to end with on this is just thinking about that plumes themselves, like treating a plume as a homogeneous mixture is maybe not the best thing. And so what Nicole's been doing lately is she's doing large eddy simulation of smoke physics and chemistry. And so this is going to animate in a moment, but the fire is here. And then there's an injection based on observations that some of it makes it into the lower free troposphere and some of it injects into the boundary layer. And what's in the boundary layer that's turbulent mixes and spreads out, and what gets injected into the free troposphere, it's quite stable and it maintains high concentration. So I'll animate it now. You can see the free tropospheric plume, high concentrations in orange. And then the lower part that doesn't make it to the free troposphere mixes and dilutes into the boundary layer. And there's actually roughly the same amount of smoke in the boundary layer as the free troposphere here, but it's just staying, it dilutes so quickly it goes to low concentrations here. There you can see the spread. So there's actually a different wind direction in the lower free troposphere, and then you get the Ekman spiral spreading things out at a different wind direction in the boundary layer. So if we take this and we imagine you have slices through this plume downwind, and we look at what curtain plots of the slices. So this is taking the slice through 8.8 hours downwind. So here's the free troposphere. This is CO concentration, so high concentrations maintained in the free troposphere and then mixing in the boundary layer. At 2 hours downwind, we're maintaining that high concentration in the free troposphere, but getting more mixing in the boundary layer. And then at 3.2 hours downwind, more of the same. And so we're getting dilution here, and we're getting much less dilution in the free troposphere. And so just circling back to one aspect of this, we're looking at many things in the plume, ozone and SOA, POA, but just thinking about coagulation, because we talked about it, high concentrations here, low concentrations here. This is what the predicted particle diameter is at these times. And so at the high concentrations in the free troposphere part, those particles are growing because of coagulation to well over 300 nanometers. They're just bumping into each other like crazy and increasing the number of concentrations. But where we have dilution in the boundary layer, those particles are staying around 200 nanometers. So same fire, same emissions in both places, significantly different properties in different parts of the plume because of different amounts of dilution. So the main thing I want you to take from this is that particle size, or actually anything nonlinear, depend on different heights or locations in the plume. So we maybe shouldn't even be thinking of plumes evolving as a unit itself, but we actually think about different parts of the plume. And so this is critical to understand concentration variability to estimate biomass burning aerosol sizes and climate effects, because what's below the clouds here is going to have a different particle size than what's perhaps above the clouds in the free troposphere. So just to summarize this part, it's really important that we get plume dilution and concentrations right for all these processes like coagulation, SOA, POA, gas phase chemistry that depend non-linearly on concentrations due to these two effects being challenging in our models. And with that, I'll just leave you with the summary slide for my talk and my main points. And thank you again for having me. Thanks.
Hi, very fascinating talk. I'm curious about, so coagulation can explain the particle growth. So condensation doesn't matter. So is that because it evaporates, compensated by condensation?
Yeah, there's sort of two parts to it. You hit the nail on the head for one of it. It's actually pretty darn fascinating. I had this in the talk, but then I'm like, oh, there's too much in the talk, so I took it out. Just how often POA evaporation roughly balances SOA formation, at least in the young plume, over the first 8-ish hours. You could get, plus or minus 10% changes in the OA enhancement ratio as a net, but often averaging to like no change when you average across many plumes. And you see the composition changing. We see it's clearly getting oxidized. It's probably getting oxidized more than particle phase or heterogeneous chemistry can explain. So there's POA evaporating, and that evaporated POA can oxidize and jump back in. And then there's VOCs that are oxidizing and coming back in. And somehow those just tend to balance on average. It's wild.
John Wang from University of Iowa. Jeff, thanks a lot for giving you an assignment for my talk on Friday. I'm not fully prepared for it, so thanks for that. I did like your talk. I think that with some experience we had this summer, we have been looking at the operational air quality forecast this summer from various models globally. And it seems to me that many of the models, all models overestimate the PM2.5, many cases. So your finding of showing the GSChem model has the injection height likely to be low, might probably spot on. Probably GSChem is better than others, but we do see almost all the models have overestimation. Another comment is that optically, there is also ground-based observation to show that the particle size vary with optical depths. So you are showing here, I find it's very intriguing, is that the particle diameter will change with a lifetime.
Yeah.
So there is some synergy there, might be provide more insight for the models. So from optical point of view.
Yeah, I showed it only a smidge there in the direct effect calculation where enhancement, because it went to larger sizes where it was right at the peak of mass scattering efficiency. But yeah, when we're looking at satellites, interpreting satellites, those sorts of things, like we have these, particle models that are assumed by the satellites, and they like these fixed sizes and stuff, but yeah.
there are aeronets, the aeronet observations that show the particle diameter changes with optical depths. So that may be something can compare to your model as well, yeah.
Thank you. Thank you.
Good.
Hi, thank you, Jeff. It's very interesting talk. I'm Lee from CRC Boulder and NOAA GSL. So I think your talk show a lot of exciting results, which can help us to improve our operational global aerosol prediction model. So I have two questions here. So you mentioned that you are testing using the GFAS data. I think the GFAS emission is somehow like daily, right? So I'm wondering, so how do you think about the diurnal cycle of the impact of this injection height on the model? Because normally the injection height may change with time in daytime and nighttime.
Yeah.
That's my first question.
We assume a diurnal cycle following climatology of based on different ecosystems. There's a different diurnal cycle, whether it's a savanna fire versus a evergreen fire, those kinds of things. But if you actually start looking at fires on satellites, there's clearly such variability in diurnal cycles, even though it does tend to peak in the afternoon on average. But like the more information we can get in inventories or in the models from satellites or other observations on like plume specific, fire specific emission rate diurnal cycles and injection height diurnal cycles, the better we'll do. And I guess to June's point before about like the forecast models having too much at the surface, it's going to help in a few different fronts. Yeah.
Okay, thank you. So the second question that you mentioned about the size distribution with this fire dilution, so it may change the size distribution. So I'm wondering, normally in our large scale wet deposition, especially in the physics part, it may change with the size distribution about this wet deposition. So do you consider that in this model?
We do when we have that in geoschem. It's fairly crude where we just say for large scale precipitation, we just say it always has a supersaturation of this, and any particle sizes that are above that supersaturation are susceptible to in-cloud scavenging, whereas everything's susceptible to below-cloud scavenging. So yeah, it would have that feedback by making them larger, changing the lifetime through changes in deposition, both dry and wet.
Hi, I'm Ben Murphy from US EPA. So thank you very much, Jeff. That was incredible as always. So I also have two questions about the subgrid scale variability or subgrid scale coagulation module. So you can answer both or pick one. One is, do you have a guess for how important that impact will be for a regional scale model? So 12 or 15 kilometers. And the second question is for the DPM, not for the starting size. Does the model just assume that all fires start at the same size distribution, or is there information going in about the fire type to know where that starting point is?
All right, so first question, I'm going to think about this as if I work for EPA. And so I'm guessing your main things, you want to get surface PM 2.5, right? Probably secondary composition and then size maybe third, other than assuming things aren't growing past 2.5 microns, but size. So if we change the size, it'll have that effect on lifetime, like the last discussion. But that'll be secondary. So the biggest thing I would guess for like a 12-kilometer regional model where you care about PM 2.5 is that if you're in boxes where there's a fire near it or in it, you're going to have variability in weather, like subgrid variability in just that surface PM 2.5 concentration, particularly for small and medium-sized fires, where you're going to have a lot of homogeneity within a grid box. And so if you're trying to see, like on a specific day, if some city in the Southeast US is getting hit by a nearby prescribed fire in the Southeast US, it's absolutely going to be subgrid scale, at least until all those prescribed fires start merging with each other, then it'll affect that. But in terms of 2.5 burden averaged over the whole Southeast US, I wouldn't expect it to be huge. There'll be some in the SOA, POA stuff that we were talking about with Manabu a second ago, but those roughly kind of kind of cancel out, that sort of thing. So I think you, in that case, are probably among the more secure in that case. And second question was, oh, remind me, sorry.
Was the starting size for the fires?
We have not made that ecosystem dependent yet. There's so much coagulation that happens very quickly that the true emission size, like if you go into some of the flame experiments in Missoula, where they like try to get the size distribution as close to the fire as possible, and they're seeing 30 nanometers, those sizes, you can't measure those in the real world because you can't get close enough to the fire to do that. And so it's hard to imagine any starting below about 100 just because of coagulation. Maybe for a campfire. So it really then I think more comes down to the emission flux, mass emissions per meter squared, and the initial dilution rate is really going to determine what your size distribution is at, say, 10 minutes downwind. It's just going to determine whether coagulation is just going nuts or whether it gets kind of shut down. More so I actually think variability in emission flux and fire size between ecosystems is going to matter more than the true initial emissions diameter because of the coagulation in the first 5-10 minutes. But that's a great question.
Thank you for the talk. I'm Karine from Syria in France. I was wondering, so you showed that the aging by coagulation is very important and it changed a lot the properties. That's very interesting. And I'm wondering, as the plume age, it moves as well. So you still, from what I understand, is you still put the plume, the age plume in the same grid box as the original one. So, but do you think that would have an impact to try to simulate where actually is the grid plume?
Yeah, that's a good point. So just to reiterate that point, we just plume for 5 hours, but then we put it at the starting point. And so there's this sort of contradiction there that we are aging it right over the fire. If you're running a coarse global model, that 5 hours of aging probably moves you half a grid box or so if you have a coarse model. So I'm less concerned about that. But if you are concerned about smoke properties at a specific location on a regional, like in a regional model where you're at 10-20 kilometer resolution, and you want to get the properties very right, within each grid box, then there would be an issue because we are saying the properties that should be happening 3-4 grid boxes down are actually at the start. Whether it happens sort of you average over the region, I don't think it would have much of an effect if we want to get sort of domain average properties, but you're right, that it's not, there's a bit of a contradiction there, yeah.
All right, I have one question from the Slido chat. So Correlating asks, how large are the uncertainties in vertical velocities and mixing in the atmospheric dynamics models compared with the uncertainties in injection height?
So first off, Kari, thanks for the question, and I hope you're feeling okay. I know you were supposed to be here. Sorry, I did not see you. Uncertainties, and then so this, I guess you're limited when dynamics models in terms of the prediction of plume height, or the dynamics in terms of lofting, like post, reach equilibrium level for the initial height and then dynamics afterwards. I'll try to answer it the first way. There is big uncertainties if you're trying to simulate the dynamics of plume rise in a model. That sort of manifests itself in the uncertainties in the GFAS emission inventory because they're using a thermodynamic model to try to determine that. And then uncertainties in large scale dynamics, probably less than the uncertainties in plume height. Is that, did I interpret it how you would have, or?
I think so. Yeah. Maybe one follow-up question that came to mind. When you think about mesoscale meteorology, people often struggle with convection schemes and thinking about clouds, for example.
Yeah.
So do you think there is a similarity with the plumes, or is it different because of the extra kind of temperature effect from the fires?
So yes, the like FreeTOS scheme that GFAS uses is just a convection scheme. So it's the same model. So we're starting with the same uncertainties. And then to your point, now we have a heat source beyond solar heating of the surface that because of the uncertainties in fire radiant power and the properties of the fire itself will add more than beyond the convection scheme. So yeah, that was a good way to frame it. Thank you.
Other questions? I have one more. One question that came to mind is also when you showed the direct radiative effects, thinking about kind of smoke above clouds versus below, how much do you think is the impact of black carbon versus, let's say, organic aerosol in these plumes and on the direct effect?
I think that's going to come down to the color of your organic carbon. And I don't know if Megan's going to talk about above cloud effects. Cool. I would expect black still wins, but the fact that you can start looking at the whole continuum between black carbon and fully scattering organic carbon is going to change that balance a bit. And you certainly, when we put a much more crude brown carbon scheme in than what Megan's going to show, we get a big change in our predicted direct effect because of putting brown carbon above clouds. Yeah. Cool. I'm counting down. I see 9, 8, 7. I'm almost off to like 6, 5. There's a clock here. And
yeah, I guess we are good on time. So if there are any other questions on the floor, feel free to ask.
Nice talk, Jeff. I could ask this anytime, but since this time, I could ask this one. So presumably you also had on FireXIQ and SP2, would you be able to see the same effect of coagulation with the BC cores coagulating?
I'm trying to remember if Nicole looked at that. My concern with the SP2 is that the size range where you can be confidently quantitative on size for the SP2 is if my understanding is relatively small. I mean, particularly compared to the bulk size distribution instruments, the LAS, the UHAS, and those things. But yeah, I'd have to think about what we'd expect to see if you looked at black carbon in isolation, because you'd be getting it, because we have this mixture of black carbon and organic carbon, and it's all mixed together in these plumes because there's so much coagulation. Is the shift going to be similar? And I know with SP2s you can also get the coating, but that's the coating thickness, and that's even a smaller size window where you can be quantitative on that. So yeah, I'm not sure, but I think it's something to be looked at. And I don't recall if Nicole did that. Maybe we didn't have the finalized product when she started. Thank you.
All right, so let's thank our speaker again. Thank you very much, Jeff. So we are having a coffee break in the lobby, and we will restart at 9:45 with the session on machine learning and data science.